A single human being steps aboard a spacecraft. They're 25 years old. The engines ignite. They accelerate to a speed so extreme that reality itself begins to break. And when they finally step off that ship, decades later, they've crossed a distance so vast that the civilization they left behind has been extinct for longer than our entire species has existed on Earth. This isn't science fiction, this is physics. Before we dive in, quick question. What country are you watching this from right now? Drop it in the comments. I'm genuinely curious where everyone's tuning in from across the planet. Here's what's going to shatter everything you think you know about space travel. Right now, at this very moment, the fastest object humanity has ever built is screaming through space at 430,000 miles per hour. At that speed, you could circle the entire Earth in under 4 minutes. You could travel from New York to Los Angeles in 7 seconds. And yet, that same spacecraft, moving faster than anything humans have ever created, still need over 6,600 years to reach the closest star to our sun. 6,000 years. So the question isn't really how far can we go? The question is, why does the universe seem specifically designed to trap us here? Why do the distances between stars feel mathematically cruel? Why does every calculation, every propulsion system, every clever engineering solution we've ever conceived still leave us stuck in our cosmic backyard? The answer is going to blow your mind. And stick around until the end, because I'm going to reveal exactly how far one human life could actually stretch across the cosmos. And the number is so extreme, so reality-bending, that it contradicts everything your intuition tells you about distance, time, and what's possible. If you want to discover the actual limits of human exploration, and you love this kind of deep dive into physics and reality, do me a huge favor. Smash that like button and subscribe. It genuinely helps this content reach more curious minds like yours. All right, let's begin. The Parker Solar Probe, launched in 2018. Right now, it holds the record as the fastest human-made object ever. 430,000 miles per hour during its closest approaches to the sun. To put that in perspective, for 200,000 years of human existence, the fastest we could travel was about 25 miles per hour, the speed of a running horse. By 1900, we hit 60 miles per hour in cars. By 1969, Apollo astronauts returning from the moon reached 25,000 miles per hour. The Parker Solar Probe moves 17 times faster than those Apollo astronauts, and it's still hopelessly, devastatingly inadequate. Here's the brutal truth. At humanity's current maximum speed, traveling for an entire human lifetime, 80 years of continuous movement at 430,000 miles per hour, you would cover roughly 3 trillion miles. That sounds enormous. It contains 12 zeros. It's a distance your brain literally cannot comprehend. And it equals roughly 0.05 light years. The nearest star system sits more than 80 times farther away. You would spend your entire existence traveling and never even come close to leaving our stellar neighborhood. Let me give you another gut punch of perspective. Voyager 1, the spacecraft that's traveled farther from Earth than any other human-made object. It's been journeying through space for 47 years, nearly half a century of continuous travel. In that time, it's covered 15 billion miles. Headlines proclaimed it left the solar system when it crossed into interstellar space in 2012. But here's the reality. That 15 billion miles represents less than 0.03% of the distance to the nearest star. If the journey to our nearest stellar neighbor was a road trip from New York to Los Angeles, about 2,800 miles, Voyager 1 would have traveled roughly 100 feet in 47 years. You'd still be in your driveway, barely past the mailbox. This is where it gets really depressing. The problem isn't just about building faster rockets. The problem is fundamental physics. Chemical rockets, the technology that's carried every spacecraft ever launched, are limited by chemistry itself. When you burn hydrogen and oxygen, the most energetic chemical reaction we can use, the resulting molecules can only move so fast. The energy released by breaking and forming chemical bonds has an absolute ceiling. The math is horrifying. To accelerate even a small probe to just 1% of light speed with chemical propulsion, you would need a starting fuel mass exceeding the total mass of the entire observable universe. Not the Earth, not the Sun, not our galaxy. Every galaxy, every star, every atom in the entire cosmos wouldn't provide enough chemical fuel. Ion engines? Too weak. They generate thrust equal to the weight of a single sheet of paper. Nuclear thermal rockets? Better, but still inadequate. Maybe 100,000 miles per hour. Journey time to the nearest star? 28,000 years. Solar sails? Elegant, but powerless once you leave the sun. Maybe 500,000 miles per hour maximum, still over 5,000 years to the nearest star. Fusion propulsion, the most realistic option we have, might reach 10 to 15% of light speed. Journey time still 50 to 80 years to nearby stars, with barely any time dilation benefit. Many 20th century physicists concluded that interstellar travel was simply impossible for biological beings. The distances seemed designed specifically to prevent life from spreading between stars. The universe had imposed a cosmic quarantine through the merciless mathematics of space and time. We can communicate with distant civilizations through radio signals that take years to arrive, but we could never visit them. We could never shake hands with an alien or walk on a world orbiting another sun. The cosmos seemed to forbid such adventures. But what if I told you there's a loophole? A loophole so profound, so reality-bending, that it transforms everything.
A 26-year-old patent clerk in Switzerland asked a simple question. What would happen if you could ride alongside a beam of light? His name was Albert Einstein, and the answer he found revealed that the prison walls keeping humanity trapped aren't nearly as solid as they appear. Distance and time, it turns out, aren't fixed, they're flexible. They stretch and compress depending on how fast you move. A clock on a speeding spacecraft doesn't tick at the same rate as a clock on Earth. Time itself slows down at high velocities. At 50% of light speed, time aboard your spacecraft passes about 15% slower than on Earth. Noticeable, but not transformative. At 90% of light speed, time dilation gets serious. 1 year for you equals 2.3 years on Earth. A 50-year journey means Earth ages 115 years while you age 50. At 99% of light speed, things get wild. 7 years pass on Earth for every year you experience. A 50-year journey spans 355 years of Earth history. At 99.99%, 70 years of Earth time equals 1 year of your life. Let me show you what this actually means. Vega, one of the brightest stars in our sky, 25 light-years away. At conventional speeds, hundreds of thousands of years. At 99% of light speed, 3.5 years of subjective travel time. You could visit Vega and return having aged only 7 years, while Earth aged 50. The Pleiades star cluster, 440 light-years distant. At 99.99% of light speed, 6 years of subjective travel. You could explore multiple stellar systems and return having aged 15 years, while Earth aged 900. The center of our galaxy, 26,000 light-years away, containing a black hole with 4 million times the Sun's mass. At 99.9999% of light speed, 37 years of ship time. You'd leave at 25, arrive at 62. Earth would age 52,000 years, but you would have lived a normal human lifespan. And here's where it gets absolutely insane. The Andromeda Galaxy, 2.5 million light-years away, a completely separate island universe containing 1 trillion stars. At sufficiently extreme velocities where time dilation reaches a factor of millions, you could travel to Andromeda and experience the journey as lasting only a few years. Earth would age 2.5 million years. Human civilization would likely be extinct upon your return, but you would have aged barely a decade. Now I know what you're thinking. This is amazing. Why aren't we doing this? The catch is energy. Accelerating to these speeds requires stupendous amounts of energy. Accelerating a small probe to 90% of light speed requires energy equal to the sun's total output for several seconds. For a vessel that could support human life, the sun's output for several minutes. We understand the physics perfectly. We've known about time dilation for over a century. The barrier isn't physics, it's engineering. Chemical rockets can't do it. Ion engines are too weak. Nuclear thermal helps but isn't enough. Fusion propulsion might get us to 15 to 20% of light speed eventually, but that's still not enough for dramatic time dilation. Antimatter would be perfect, but we can only produce about 10 to 20 nanograms per year, and we'd need kilograms or tons. But here's the thing, the laws of physics don't prohibit this. The universe permits velocities arbitrarily close to light speed. The only limit is the energy available for acceleration. Which brings us to the answer you've been waiting for. Remember that moment at the beginning? A 25-year-old human boards a spacecraft, accelerates to extreme velocity, and when they step off decades later, they've crossed distances so vast that the civilization they left behind has been extinct for longer than our species has existed. Here's the full picture. At the most extreme relativistic velocities, where gamma factors reach hundreds of thousands or millions, a single human lifetime could theoretically span distances of billions of light years. You could travel from one end of the observable universe to nearly the other. You could visit galaxy superclusters containing thousands of galaxies. You could witness cosmic structures spanning hundreds of millions of light years, all within 50 to 80 years of subjective time. But there's a cost that has nothing to do with engineering. Every journey becomes a journey forward through time. You cannot return to the era you departed from. Time dilation allows you to age slowly while the universe ages rapidly, but it doesn't let you go backward. A round trip to the galactic center, you return to Earth 520,000 years in its future. Modern humans have only existed for 300,000 years. A round trip to Andromeda, 5 million years would pass on Earth. 5 million years ago, humans and chimpanzees hadn't even diverged. You would return to a world as alien to your departure era as we are to ancient apes. Even with perfect propulsion, there's an ultimate limit. The universe itself is expanding, and that expansion is accelerating. This creates something called the cosmological event horizon, currently about 16 to 17 billion light years away. Beyond that boundary, cosmic expansion wins. Space stretches faster than any velocity could overcome. No matter how fast you go, no matter how long you travel, destinations beyond that horizon are impossible to reach. And that horizon is shrinking. In 100 billion years, only our local group of galaxies will be accessible. Every other galaxy will have crossed beyond reach forever. We're living in a brief window of cosmic opportunity. Every galaxy we see will eventually become unreachable as expansion carries it beyond the event horizon. So how far could a human actually travel in one lifetime? The physics says nearly anywhere in the observable universe, given sufficient velocity. The engineering says we can't build the propulsion systems yet, but nothing prevents us from eventually doing so. The cosmos says most destinations are already lost to expansion, but billions of galaxies remain theoretically accessible. And the human heart says every journey towards the stars is also a journey away from home. The farther you go, the more you sacrifice connection to everything you've ever known. The universe hasn't built walls around humanity. It's built highways stretching towards every horizon, highways we haven't learned to travel yet, but that physics declares open to anyone who can master the necessary velocity. The stars aren't impossibly distant, they're just waiting for us to develop the means to reach them. If this video bent your brain even a fraction as much as researching it bent mine, hit that like button. Subscribe if you want more deep dives into the nature of reality, and drop a comment. What would you choose? Would you take a one-way trip to Andromeda knowing you'd never see Earth again, or would you explore closer to home, keeping some thread of connection to humanity? I'll see you in the next one.